Hi again, this is endocrine lecture number 3, the adrenal gland, the pancreas, which is the one that I could not think of earlier, and we're going to talk about the stress pathway. Learning objectives or performance objectives, and right into the adrenal gland. The adrenal gland has two parts, the adrenal cortex and the adrenal medulla. Just like the thyroid had follicular cells and extrafollicular cells that secreted different hormones, the adrenal gland does the same thing. So the adrenal medulla is this interior portion of the adrenal gland, and it is made up of cells called chromaffin cells. And the chromaffin cells are special because what they basically are postganglionic neurons, okay? So think back to the nervous system, to the sympathetic motor division of the nervous system. You had preganglionic neurons and postganglionic neurons. And for the sympathetic system, the postganglionic neurons released norepinephrine, and it had its effects all over the body, and its fight or flight kind of effects, stimulating heart rate, making your breathing faster, so on and so forth. When the sympathetic nervous system comes down here to the adrenal gland, the norepinephrine is released from the adrenal medulla as a hormone that goes into the blood, not as a neurotransmitter that acts directly on an effector. Okay? Same norepinephrine, same substance, but it goes into the blood and that makes it a hormone. Okay? So this is still part of the sympathetic nervous system. For the adrenal medulla, you can basically consider it almost like part of the nervous system, but it releases norepinephrine as a hormone. Okay? The adrenal cortex is this outer portion. And if you see it over here, they've taken a little slice, okay? It's the thicker the thicker portion, and it's in 3 distinct layers: the zona glomerulosa, the zona fasciculata, and the zona reticularis. The hormones from the adrenal cortex do not respond to nervous stimulation. They respond to the hormone adrenocorticotropic hormone, or ACTH. And you should remember from the anterior pituitary gland that ACTH is an anterior pituitary hormone stimulated by the hypothalamus, by CRH from the hypothalamus. So again, it's nervous control, but it's not direct. So it's coming from the hypothalamus and the pituitary gland. The ACTH comes down and stimulates the cortex to secrete its own hormones, while the adrenal medulla is stimulated directly by neurons coming from the sympathetic nervous system. So I'm going to kind of repeat myself a little bit here. The adrenal medulla is an integral part of the sympathetic nervous system. Its chromaffin cells produce, store, and secrete norepinephrine and epinephrine. So chemically, norepinephrine and the hormone norepinephrine and the neurotransmitter norepinephrine are the same. It's the same exact chemical. So how are they different? Well, one is released from the end of a neuron directly onto its effector. Okay, could be your heart, could be your lungs, could be your bladder, right? Whatever muscle is affected, irises of your eyes, by the norepinephrine, by the sympathetic stimulation. The difference is the hormone norepinephrine is dumped into the blood. So that says something about how long it takes to act, because it's going to take longer, right? It's not a neurotransmitter. It's not hitting its effector right at the other side of the synapse. It's going into the blood and it's traveling. It takes longer to get to its effector cells, and it lasts longer because it circulates in the blood for a long period of time. So while the nervous stimulation, the nervous part of the fight or flight response from the sympathetic nervous system is really quick, if it activates the adrenal medulla to release norepinephrine into the blood, then you're going to have a much longer response. The effects of norepinephrine, we know them, we've talked about them a lot, okay? Increasing heart rate, increasing blood pressure, getting your body prepared for that flight or fight response. That's true whether it's a hormone or a neurotransmitter. And so this hormone really is kind of a stress response, a physical stress or a mental stress, an emotional stress, but you're going to have a stress response. Now, the difference between norepinephrine and epinephrine, okay, these are both adrenal medulla hormones. There's not a huge difference. They stimulate different types of receptors. The receptors that norepinephrine stimulates are called alpha receptors, and the receptors that epinephrine stimulates are called beta receptors. If you guys have heard of beta blockers, which I bet a lot of you have, beta blockers are drugs that are given often for high blood pressure. So a beta blocker blocks the effects of epinephrine, right? Because epinephrine needs beta receptors to increase your heart rate, to increase your blood pressure. If you block the receptors with a beta blocker, then epinephrine won't have such a potent effect. The adrenal cortex, okay, so this is the one that is the outer portion of the adrenal gland that is under the control of the pituitary gland and the hypothalamus, secretes a few hormones. One of the most important is aldosterone. Aldosterone is a mineralocorticoid, okay, which means it regulates the concentrations of mineral electrolytes, so important minerals including sodium and potassium. Right, so if you remember that it's a mineralocorticoid, you can remember that it regulates sodium. Specifically, if you have aldosterone going through your system, you are going to cause the kidneys to conserve or retain sodium and excrete potassium. But you want to keep sodium. If you need to keep sodium in your system, you'll secrete aldosterone. However, it's an indirect action, and this is where this gets a little bit complicated. But aldosterone works through something called the renin-angiotensin system. So, first off, and this is kind of basic, think about the effects of sodium in the blood on just osmotic pressure and blood pressure, okay? We know what osmotic pressure is. If there's more osmotic pressure, which means there's more solute, or sodium could be a solute, then you hold on to water. Water follows salt. So if you have a lot of salt in your blood, you're going to retain water, and your blood pressure is going to go up. So understand that increased sodium increases blood pressure because excess sodium in the blood causes water to be retained, right? That's the effect of ADH. The osmoreceptors sense high osmotic pressure, they retain water. That's going to bring your blood pressure up. Okay, so understand that to begin with. Now, if your blood pressure or your sodium ion concentration go down below normal levels, okay, lower. So this is not, we don't want to decrease blood pressure here. We actually need to increase it. Then your kidney will start this renin-angiotensin system, okay? What I want you to take from this is that when your kidney senses decreased blood pressure or sodium ion concentration, it will secrete renin. And then there's this huge pathway whereby renin gets converted and converts angiotensin into angiotensin, blah, 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 blah. You don't need to know that in detail, okay? But this pathway eventually stimulates the adrenal cortical cells to secrete aldosterone, okay? So it's angiotensin that actually stimulates the adrenal cortex. Aldosterone is released into the bloodstream. It acts on the kidney to conserve sodium, and then if you're conserving sodium, you're also conserving water because that just happens with osmosis, okay? And then your blood pressure and your sodium ion concentration return towards normal and inhibit further secretion of renin. So it starts in the kidney with the secretion of renin. This process happens in the blood. Angiotensin stimulates the cortical cells of the adrenal gland to secrete aldosterone. Aldosterone causes the kidney to conserve sodium. If you're conserving extra sodium, then you're going to conserve water. And that is the pathway of the renin-angiotensin system. So the question I have for you is, how can you treat an individual with high blood pressure or hypertension, so someone with chronic high blood pressure using this system, okay? So I want you to, again, think about that. We'll talk about it on Tuesday. So that's the aldosterone, right? The other adrenal cortex hormones are cortisol, and then some quantities of adrenal androgens. Androgens are sex hormones. They're very small quantities from the adrenal glands, but you should realize that they actually do come from the adrenal cortex to some degree. Okay, cortisol. Cortisol is kind of similar to aldosterone structurally, but it is a glucocorticoid. It affects glucose, protein, and fat metabolism, right? It's also a steroid hormone. And the three ways that it affects glucose, protein, and fat metabolism are to inhibit the synthesis of proteins, which increases your free amino acid concentration, because of course proteins are made of amino acids. It stimulates liver cells to synthesize glucose from non-carbohydrates. That's called gluconeogenesis, new creation of glucose. So it can use free amino acids or lipids or some other things to make glucose. And it promotes the release of fatty acids from adipose tissue, which makes you use them as an energy source instead of glucose. So you're decreasing glucose utilization for energy. So overall, what you should take from this is that the goal, when you have lots of cortisol getting released, is to spare glucose and reserve it for use by the brain. Okay, so in periods of stress, your body's like, hey, something is going on. We need to save glucose and use it for the brain, because you got to keep your brain alive at the expense of everything else. During normal days, you have cortisol anyway, even without stress, and it just maintains your blood glucose concentration between meals. So if you go like 4 or 5 hours between eating, you exhaust your glucose stores pretty quickly from your last meal, and you exhaust your glycogen. And so cortisol would be secreted to kind of keep a little glucose boost until you can eat again. Cortisol is also used as an anti-inflammatory and an immunosuppressant. So both of those things, those are kind of targets for synthetic glucocorticoids. So prednisone is a really common drug to reduce inflammation and to suppress the immune system. So it's a treatment oftentimes for autoimmune disorders like rheumatoid arthritis, where your body is attacking itself. You can give a glucocorticoid and like prednisone, and that will help suppress the immune system and keep that disorder at bay. So here's the cortisol negative feedback loop. Under stressful conditions, CRH from the hypothalamus is increased, and that leads to ACTH to be released from the anterior pituitary gland, and of course that gets dumped into the bloodstream. ACTH stimulates the adrenal cortex to release cortisol. Cortisol goes into the bloodstream, and it has the effects that I just mentioned about inhibiting protein synthesis, stimulating glucose formation, promoting fatty acid release, and cortisol then inhibits the secretion of CRH and ACTH. What happens to this cycle if you put a patient on a high dose of prednisone, which is a synthetic cortisol? And then if you suddenly take the prednisone away. Again, these are questions that I want you to think about, and we will discuss. So there are a few adrenal disorders worth mentioning. The first is Addison disease, in which the adrenal cortex does not secrete glucocorticoids or mineralocorticoids sufficiently. And symptoms of that include salt cravings, because you're going to crave salt because your body wants salt so it can hold on to water. Hypoglycemia, low blood sugar, dehydration, low blood pressure, etc. And you treat Addison disease simply by giving the glucocorticoids, the mineralocorticoids that are not being produced naturally, and you can kind of even that out. Cushing syndrome is the opposite. It's hypersecretion of adrenal cortex hormones. This is very rare to occur naturally, but it often occurs with long-term synthetic glucocorticoid use. So long-term use of prednisone or some other glucocorticoid is actually really dangerous because you are, inhibiting protein synthesis and breaking down lipids really rapidly. Symptoms include weight gain, fat deposition around the face. So you actually break down those lipids and you mobilize them and you put them other places. It thins your skin, you get easily bruising, abnormal hair growth. I'm not 100% certain of all the mechanisms behind those things. Cortisol is something that is really pretty complicated, actually. It affects lots of systems. But if you have too much of it, it's really not a good thing. So you don't want to be on long-term synthetic glucocorticoid use. And also, like I mentioned above, or like we're going to discuss about on Tuesday, the risks of being on prednisone for long periods of time. We'll go over that again. So treating this, removing the glucocorticoids if they're synthetic, if they're being added externally. And you can also, if it's a naturally occurring thing, actually remove one of the part or a whole one of the adrenal glands to try and cut down on the release. So while we're talking about the adrenal gland, I want to talk about the stress pathway. What is a stressor? Okay, stressors can come in a variety of forms. They can be physiological and they can also be psychological. So you can have a physiological stress like cold or injury. You can have a psychological or emotional stress like a final exam. The brain region that is responsible for the stress response is the hypothalamus, because the hypothalamus is the brain region that goes on and stimulates the ACTH and the norepinephrine and everything else. The arm of the nervous system, of course, is the sympathetic nervous system. The endocrine glands involved, well, the hypothalamus, the anterior pituitary gland, and the adrenal gland. And the hormones that are secreted. So remember, you have not only nervous system sympathetic effects that are secreting norepinephrine as a neurotransmitter, but you have norepinephrine and epinephrine as hormones, and you also have CRH, ACTH, and cortisol involved in the stress response. So I'm going to show you a better graphic on the next slide. Okay, together these systems comprise something known as the HPA axis, which is the hypothalamic pituitary axis, and that regulates the stress response. And here it is, the stress pathway. So stress results from changes in the internal or external environment, and that signals your sensory receptors. And that triggers the hypothalamus to do a few things, okay? First, really quickly, you have sympathetic impulses going. They show two branches here. They show them going to the adrenal medulla. And that makes sense because the adrenal medulla has those chromaffin cells in it that release norepinephrine and epinephrine as hormones, right? Additionally, norepinephrine gets released as a neurotransmitter at the heart, at the lungs, at the diaphragm, at all of these different areas of the body where you have this kind of alarm effect, right? So the short-term fight or flight or the alarm stage, what happens really quickly, blood glucose increases, glycerol and fatty acids increase, heart rate increases, blood pressure increases, breathing rate increases, air passages dilate, pupils dilate, blood flow redistributes, goes away from your gut and to your legs so that you can run. And that's the alarm phase, okay? The sympathetic nervous system and the effects of the adrenal medulla are really fast. The effects of the adrenal medulla are slower and longer lasting than these, but they still fall into the fast arm. On the other hand, the hypothalamus releases CRH, and that travels to the anterior pituitary, which releases ACTH, which travels to the adrenal cortex, which releases cortisol. And this is the long-term adjustment or resistance stage, okay? Cortisol causes the blood concentration of amino acids to increase, it releases more fatty acids, and it forms more glucose. So this is when your body is going, okay, I can deal with this stress. I'm going to adapt to it. This is not blood pressure, breathing rate, ready to fight or flight. This is, okay, I have an exam in a week. I'm a little stressed out about it already, but we're going to have some resistance. Your body's going to adjust and you're just going to deal with it. So the stress pathway is adaptive, okay? It's adaptive response to immediate stressors. It's good, right? This is normal. It's normal to be a little stressed. That's what I always tell people when they're like, oh, I'm so stressed out. Well, if you weren't, something was wrong. Okay, this is good. But what would happen to this pathway in response to chronic stress? Okay, if you are stressed chronically for long periods of time, and I'm talking real stress, like I can't even think of a nasty enough example without being morbid, but being held captive would be chronic stress, really long-term chronic stress. You're going to have a whole lot of activity in this pathway, and long-term stress, excuse me, we've seen before that long-term stress and high concentrations of cortisol can have some really negative physiological effects. So I think we'll talk about that a little more on Tuesday too. Specifically, you guys that are going to get assigned to the HPA axis or the CRH, ACTH, and cortisol hormones for the wiki are going to have some really interesting things to share about stress, I think. Last major endocrine gland that we're going to cover is the pancreas. The pancreas is an endocrine and an exocrine gland. And what is the difference? Exocrine glands release their fluids onto body surfaces. Endocrine glands release their hormones into blood. How is the pancreas also an exocrine gland? Because it has these ducts, here they are, that secrete digestive juices into the small intestine. More on that when we do the digestive system, but that is its exocrine function. It also has pancreatic islets, okay? These are the hormone secreting cells in these islets. And there's 3 endocrine cell types in the pancreas. The alpha cells, which secrete glucagon, the beta cells, which secrete insulin, and the delta cells, which secrete somatostatin. What is the primary role of pancreatic hormones? What does the pancreas do? The pancreas regulates blood glucose levels. How much sugar you have in your blood. Blood glucose too low, right here, that's your stimulus. Your receptors are alpha cells. They sense that decrease in blood glucose and they stimulate the alpha cells to secrete glucagon. Glucagon is the effector. It stimulates liver cells to break down glycogen into glucose and convert non-carbohydrates into glucose, and your blood glucose level returns to normal, which then inhibits glucagon secretion. Blood glucose too high, the glucose level increases. Your beta cells sense that increase in blood glucose, and the beta cells secrete insulin. The effectors, insulin promotes the movement of glucose into certain cells and stimulates the formation of glycogen, and the blood glucose level returns towards normal. So the major disorder of pancreatic hormones, of course, is diabetes. About 21 million people in the United States have diabetes. That is almost 10% of the population, and there's estimates that lots of people have the disease but haven't even been diagnosed. And then there's another 80 million people that are estimated to be pre-diabetic. So we're talking a huge 100 million people kind of crisis of this disorder. Diabetes arises from a complete lack of insulin, that's type 1 diabetes, or an inability of the pancreas to produce enough insulin that the body needs, and that's type 2. So if you don't have insulin, then you're not converting your glucose into glycogen and you're not storing it, and it accumulates in the blood. The kidneys start to excrete it. That's one of the first signs of diabetes. Because they're excreting glucose, they're losing a lot of water, okay? So that's just osmotic pressure. Water follows solute. Kidneys are getting rid of glucose. The water is going with it, getting rid of H2O as well. And that results in really dangerous dehydration. You don't have all that glucose, so your cells are starved and they start using proteins for energy and your tissues waste away. Disruptions in fat metabolism causes fatty acids and ketone bodies. Ketone bodies are acidic and they accumulate in the blood, and that lowers your blood pH, which is called acidosis. It is a very dangerous condition. Dehydration and acidosis harm your brain cells. They cause disorientation, coma, and eventually death. So this is untreated diabetes. Very, very dangerous. Lucky for us, we have been able to treat it fairly easily thanks to the use of biotechnology to produce really large quantities of human insulin. So now people that have type 1 diabetes, which has no known exact cause, with insulin, and they can regulate their insulin levels and live relatively normal lives. And type 2 diabetes, which is usually associated with obesity and a sedentary lifestyle, can also be treated with insulin, but can also easily be treated with dietary and lifestyle changes to a large degree. Okay, other endocrine glands, there are a few more. The pineal gland produces something called melatonin, which regulates your circadian rhythms. It's for sleeping, okay? Lots of people take melatonin in a pill form to try and help them sleep, but your body does produce it naturally in your pineal gland, which is in your brain. Your thymus, which is kind of lower in your chest than your thyroid, plays an important role in the production of T lymphocytes for the immune response, and we'll talk about that a little bit when we talk about the lymphatic system. And then, of course, your reproductive organs and the placenta, which is an organ that's formed only during pregnancy, for the secretion of sex hormones. And we're going to hit these pretty hard in a couple months. So that's the last slide. If you can think of any questions, again, please write them down. I have asked you a few questions and to think about a few things. I'll ask them to you again on Tuesday so we can discuss them before we go ahead with our projects. Thank you for listening.